Today we're going to talk about complex numbers. Complex numbers are of the form a plus bi. A is the real part, and bi is the imaginary part. So we could have numbers that were purely real if they were just a. We could have numbers that were purely imaginary, just bi. And then we can have numbers that are part real and part imaginary, which are called complex numbers. So why did complex numbers arise? Well, problems like the square root of 9, which we know is 3, piece of cake. All of math history, that's just been true. But then we had problems like the square root of -9, which we said, well, you can't take the square root of a negative number. And someone said, well, why not? Let's just say that it's like 3, but it's imaginary. Okay, so what we have is we have, let's move these down, I, which is defined as the square root of -1. Okay, so technically what happened here was we said that this was the square root of 9 times -1, and the square root of 9 is 3, and the square root of -1 is I. That's how that happened. Okay, so we have I, which is the square root of -1. I squared would then be the square root of -1 squared. So I squared is actually -1. I cubed, if ever we saw it, might be, let's say, I times I squared. So it would be I times -1, so negative I. I to the fourth might be I squared times I squared, which would be -1 times -1, or 1. So we use I. When we see I squared, we say -1. When we see I cubed, we say negative I. When we see I to the fourth, we say 1. And then it keeps cycling. So I to the fifth might be I to the fourth times I. So 1 times I. So that would be I. I to the sixth might be, oh, I could say I to the third times I to the third. Lots of ways I could say it. So that would be negative I times negative I, which would be positive I squared, which would be -1. That was a lot of work but it's just cycling back through. It's going through I, -1, negative I1, I, -1, negative I1. So there's a cycle of I's, but technically there's only I, -1, negative I1 for any power of I. Okay, so let's work some problems. The directions might say simplify. So this would be 3 plus square root of -16, so 4i. This would be -4 times I squared, which is -1, plus 2i. So that would be 4 plus 2i. To subtract, let's see, I add the opposite. And then I put like terms together. So real to real, 18. Imaginary to imaginary, -8i. Multiplying is like multiplying two binomials, because they are. There's a real and an imaginary, a real and an imaginary, so they're binomial. So 13 times -5 would be -65, plus 13 times 6, let's see, that would be 78i. -2i times -5, so plus 10i, minus 12i squared. So I have -65 plus 88i minus 12 times -1, -1. So that would be plus 12. So -65 plus 12 would be -53 plus 88i. Well, that was a lot of work. I think because I gave myself big numbers. This would be 8 plus, let's see, square root of +18 would be 3 root 2. but it's negative 18, so I. This would be, let's see, square root of 5i times the square root of 10i, which would be the square root of 50i squared, which would be 5 root 2 times negative 1, so negative 5 root 2. Now you might have said, well, I multiplied them at the start and got the square root of 50. So I just got 5 root 2. The problem with that is because there are i's involved, this is not a legal first step. We'd have to actually extract the i's before we multiply. Okay, squaring, so we'd get 4 minus 6i minus 6i, so minus 12i plus 9i squared. So that would be 9 times negative 1, so negative 9. So negative 5 minus 12i. This is an interesting problem because we sometimes look at this and say, oh, it's the difference of two squares kind of look, and it is. For complex numbers, this is called the conjugate. The real part is the same, but the imaginary part is the opposite. And interesting things happen when you multiply a complex number by its conjugate. So this would be 4 plus 6i minus 6i minus 9i squared. So plus 9. So this would be 13. When you multiply a complex number by its conjugate, you always get a real number. Okay, suppose I wanted to rationalize the denominator. Okay, that's imaginary, so it's not rational. So if I multiply top and bottom by I, you might have wanted to multiply by 3i, and that would just cause you to have to simplify at the end. We get 50i on top, 3i squared, so negative 3 in the denominator. So we might call this negative 50i over 3. Here, we've got a binomial denominator. In order to rationalize that, if I just multiplied by I, it would become I plus 2. What I have to multiply by is the conjugate. Real part stays the same. Imaginary part is its opposite. Okay, so on the bottom, I'm going to get 1 plus 2i minus 2i minus 4i squared. So 1 plus 4, 5. In the numerator, I've got a small FOIL problem, so I've got 6 plus 12i minus 7i minus 14i squared. So 6 plus 14, 20. Ooh, oh dear, 20. Sorry, 20. 12i minus 7i, so minus 5i. My binomial numerator, I could factor out a 5 and get 4 minus I over 5, and the 5's will cancel. So my answer to this is 4 minus I. Solve. I guess this is out here because the quadratic formula can yield things that are complex as answers. So x equals opposite b. Oh, I might as well just do the work while I'm here. X equals opposite b plus or minus square root b squared minus 4 times a times c all over 2a. Negative 6 plus or minus the square root of negative 4 over 2, which would be negative 6 plus or minus 2i over 2. I can factor out a 2, negative 3 plus or minus I over 2, and it will cancel. So my solutions are negative 3 plus I and negative 3 minus I. These are my x equals, my solutions, my zeros, if you will. Okay.